Rather predictably in summer, one of my solar lights has failed. Well, I've been doing general solar lighting maintenance, and one of my favourites has failed, and this one has already made an appearance in this channel. It had a problem. The first problem it had was the LED in it failed, and the circuit board had a surface mount chip in the middle, and all I did was I put a little bit of Captain tape at the back here because it doesn't run the LED too hard, and I just soldered a 1 watt LED across it to replace it and get it going again. It worked very well. This incidentally has a nice glass patterned diffuser. That's not really a diffuser, is it? Lens, I suppose. But this time it was a completely different fault. The solar panel on top had finally given up the ghost. Water had seeped in. Although I'd put glue around to try and seal it, water had got underneath and it had eroded around the positive and negative contact. It had just eaten away at the metallization to the point that it was still putting out a voltage, but under any load the current just plummeted to pretty much zero. It was very low current. So I was looking to see what I could do with this. And I had a few of these with a project recently, this solar-powered automatic light where I'd stuck a lithium battery onto the back of a solar panel. I bought a couple of these solar panels from eBay, and it just turns out that they're the perfect size to replace it, an exact fit. So I glued it in, and I used silicone for that. And unfortunately, it's the acid-curing silicone, but it's the only stuff I can really get easily locally. I can't get the sort of like the neutral curing silicone that's better for electronics. But this is the acetic acid liberating stuff. I got it from Felton's, the ironmonger in Ramsey on the Isle of Man. And I put the solar panel in, glued it in, and then I wanted to seal around here as well. But when I did, there was quite a sort of like pool, if you will. The solar panel was well below the surface. So I thought, is there any way I could maybe actually put silicone across that? And the first thing I tried, I actually squirted silicone out the silicone gun backwards and forwards, and just sort of, then I got a bit of circuit board material and spread it, and that wasn't the correct way to do it. In hindsight, it trapped a lot of air bubbles because it hadn't been put on very evenly. In hindsight, the best way to do it, I think, is to do it in the style of plasterers or floor people who are putting the screed on floors, and actually put a layer at one end and then drag it across. And that way you're going to press it in without getting the bubbles, and then you can do multiple layers like that. I ended up going in all directions with this. So there is a thin film that I deliberately left on top just to seal over completely. But that is now spongy silicone all the way through to the solar panel. And then I thought, is that really going to attenuate how much charge comes off this? So I went out in the sunshine and I've stuck a couple of leads in the back of it and measured and got a current of about 85 milliamps in bright sunshine. And then I got the matching solar panel and stuck the same leads across it, same meter, went out in the sunshine, exact same position, and once again, exactly 85 milliamps. You may notice a little change in the lighting. I've got a little experimental lighting set up here, a new shelf for the camera. Took a bit of faffing around. It wasn't ideal for the job, but it's worked. So the silicone doesn't actually block much of the light at all. The current was exactly the same. And theoretically now, this is going to, well, silicone is very stable to ultraviolet energy. So I wonder how long this is going to last. I wonder if the acid liberation, you always get a slight residual liberation for a while. I wonder if will penetrate through the resin of the actual solar panel and affect it. I suppose there's only one way to find out, and that's time. Smells a bit vinegary. This is the circuit board of this. It uses a lithium iron phosphate cell. I always call it lithium ferrous phosphate. It's lithium iron phosphate, Life PO4, which is a more stable version of the standard lithium cell. This one's a 14500, which means it's 40 millimeters diameter by 50 millimeters long. And the advantage of this over standard lithium ion type cells is that although it charges to a lower voltage and has lower capacity, it's much more stable. It will handle a lot more charge and discharge cycles. It also has less tendency to explode in flames when it goes wrong, which is quite good. If you've got two identical cells, you've got the Life PO4 and you got the standard lithium, and you started off in an application, initially the standard lithium one would have much higher capacity But over time, it reduces in capacity quite quickly, and it would very quickly match this one for capacity, and then this one would overtake because these just have a much higher cycle life and shelf expectancy. So this gets charged. The LED has lit because there's no solar panel to keep it off. This gets charged by an interesting circuit in the back here. It has a shunt in it. There's a 10 ohm resistor on the back in series with the solar panel. And once the voltage exceeds the cell voltage, once the cell voltage reaches its peak, its maximum charge, which is 3.65 volts in the case of lithium iron phosphate, a little shunt turns on in this, and it dissipates the output from the solar panel just as heat to drag the voltage down to the point it won't actually put any more current into the cell. And the little resistor under there gets quite hot, but not excessively hot. I measured it with a thermal imaging camera. It was about the peak at the emulated temperature from the emulated light output from the sun and the current output from the solar panel. It reached about 70 degrees Celsius, although having said that, it's going to be in a solar light that's already getting quite hot in the sunshine, but it is just a resistor. So this one actually has two, it's got a winter setting and a summer setting with intensity. I could show you that right now. That's the, I can't show it anymore because the light's above. That's the summer setting and that's the winter setting. You're not really seeing this because it changes the intensity, which ultimately changes the discharge current, and it means that in summer, when you're getting much more sunshine, it runs the LED at higher current because it knows that it can do so for longer when you set it to that, because the cell will have taken more charge from the sunlight. But this is going to be put back together now and put outside, and we'll see how well this silicon-covered cell does. It might be an interesting way just to screed over the top with silicon over other lights just to make them resilient to moisture ingress too. So we'll see how that goes.